Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with numbers 8, 9, and 10 on your Unit 7 homework over thermodynamics. So let's see, what it says in number 8, water flowing over Albright Falls in Yellowstone National Park drops 79 meters. So I started this, just like I start about everything, with a quick little picture here. So in this problem, this distance here is the 79 meters. It says, if all of the water's energy goes into heat, what is the temperature increase? So here's what they're referring to. They're referring to the change in potential energy as the water goes from here to here. Now, it doesn't say anything about mass in this problem, but let's just start with this. Imagine a small part of this water here. Now, how much of it doesn't matter. We'll just imagine an amount m. The potential energy of this mass relative to this surface can be calculated, equal to mgh. Now you can't get a number here because we don't have a definitive amount for the mass. Just leave this alone. Leave the m there just the way it is. G is 9.8 meter per second squared. H is 79 meters. So what this is going to look like is it's going to look like now a number times m, where m is the mass. Now the question is asking you to assume that this potential energy, as the water drops, gets converted to internal energy, making the temperature of the water go up. So the relevant concept there is specific heat. So write out Q equals mc delta T. And if we assume all of the potential energy goes towards heat, that means that this is going to go here. Now at this point you'll notice there's a mass on the left and there's a mass on the right. I'll let you think about what will happen there. Specific heat is the specific heat of water, 4186 joule per kilogram degree centigrade, and then you're going to just solve for the delta T. All right, that should be enough on that one. Number 9, let me clear my pad here. Okay, number 9 says, what is the maximum efficiency that a heat engine could have when operating between the normal boiling and freezing temperatures of water? All right, so this is a question about heat engines. So hopefully you've watched my videos on heat engines. Here's kind of a schematic for a heat engine. The circle here is representing the heat engine. What a heat engine does is it takes heat from a hot source, and you usually call that heat Q sub H. It converts some of it to work, and it expels heat to some cold source. We usually call that Q sub C. The efficiency of a heat engine is what you get out, that's the work term, divided by what you get in, or what goes in, that's Q sub H. Basically the Q sub H here is what you have to pay for. Now, when we look at this, there's an energy balance. We can also write out that the energy going into the heat pump, that's the heat engine, that's Q sub H, has to equal the energy going out, which is the sum of these two things, work plus Q sub C. If you solve this for the work term, you get Q sub H minus Q sub C. And if you sub this here, the efficiency is now going to read Q sub H minus Q sub C over Q sub H. Now, you might be wondering none of these numbers given in the problem. Well, that's true, but the question asks for the maximum possible efficiency. I want to read exactly how that's worded again. What is the maximum efficiency that a heat engine could have? So the maximum efficiency is calculated by using what's called the Carnot efficiency. And you get the Carnot efficiency just by replacing the heat terms with the temperatures. So wherever you see a Q sub H, you put T sub H, and whenever you see wherever you see Q sub C, you put T sub C. So the Carnot efficiency of this heat pump is equal to T sub H minus T sub C over T sub H. Again, if you go back and review my videos on heat pumps and maximum theoretical efficiencies. So the one thing you have to be careful of is the temperatures. This law is, again, referred to an absolute law. They have to be in kelvins, have to. You cannot put the temperatures given in the problem in there because they're in degrees centigrade. It says the freezing point of water, that's 0 C. You're going to have to calculate that temperature in Kelvin. I'm going to let you do that. I'll talk about how to do it in just a minute. And it says the boiling point of water, that's 100 degrees C. and you got to get that temperature in Kelvin as well. So this one's going to be your T sub H right here. I'm sorry, this one will be your T sub C, this one will be your T sub H. And here's how you get these. Your temperature in Kelvin is equal to your temperature in centigrade plus 273.15. So you're going to take the 0, that's going to go there, calculate your temperature in Kelvin. You're going to take the 100, that's going to go there, calculate your temperature in kelvins. And that's going to be your T sub H and your T sub E, and that's how you get your theoretical efficiency. All right, so 8, 9, now we'll chat about 10. All right. Number 10, let's see. A proposed ocean thermal energy conversion system is a heat engine that could operate between the warm water at the surface and the cool water 1,241 meters below the surface. What's the maximum possible efficiency for this? So this is pretty much an identical problem. So efficiency can be calculated. I'm going to skip the pictures. Q sub H minus Q sub C over Q sub H. However, this gives actual efficiency. The maximum possible is calculated by what's called your Carnot efficiency. And that's equal to T sub H minus T sub C over T sub H. You're going to get these values from the problem, but you got to make sure they're put into kelvins. You're given two temperatures, 19 degrees C and 3 degrees C. So what you need to do is calculate the Kelvin equivalence of these using temperature in Kelvin is equal to your temperature in centigrade plus 273.15. So put this value here, calculate your T sub C. That's going to be this number. Put this value here, and you're going to be calculating T sub H, which is going to go here, and then you'll get your Carnot efficiency. You're going to end up with a pretty small, kind of dismal looking efficiency because this is not a very massive temperature change to run an engine off of, right? So anyway, that should be enough on number 10. I think I'll just stop that video right there. I hope this helps you get these done. Have a great day.